Hello everyone, a very good evening to all. Can you see my screen? Hello, am I audible? Hello everyone, can you hear me? Anyone? Hello, is my voice clear?
Clear, sir.
Okay, thank you. So we'll wait for a few minutes more and then we'll start at 7:10 or so. Because students are still joining, so let's wait for them and then we will start after a few minutes. So does anyone have any query or any doubts regarding the previous two sessions we have taken? And also I have uh, in the discussion forum of the course Experimental Physics 1 in the NPTEL site, I have uploaded the links for the drive folder in which I am uploading the presentation slides after the session is over. So if you are unable to get the files, then tell me, or if you are getting it, then it's okay. So basically I have shared a file also. It has all the links, like the link to the YouTube channel where I am uploading the videos after the sessions, and also different presentation slides. So you can go to the discussion forum in the course page and then you can access from there. Can you see my presentation? I have shared the screen. Can you see the presentation slides?
Yes, sir. Visible, sir.
Okay, thank you. So I think we should start now. So once again, hello everyone. A very good evening to all. I, Vivekananda Naik from IIT Delhi, a PMRA PhD research scholar, welcome you to the third interaction session on the NPTEL course Experimental Physics 1, which is being flowed this July 2023 session. So in the last class, we had discussed a few problems regarding the measuring devices like slide caliper, screw gauge, and also we discussed about the moving coil galvanometer and how moving coil galvanometer can be used as a voltmeter or as an ammeter. So we had discussed a few problems regarding the uh, conversion of galvanometer to ammeter. So today we will solve a problem related to the voltmeter, and then we will go forward with our discussions. So I think my voice is clear to all of you. Is it okay? And you can see the screen properly. Please, everyone, mute yourselves. Uh, in the last class, we had discussed about the galvanometer being used as a meter, which is used to measure current in a circuit. Galvanometer is used to measure very small deflections like small current or small voltage. But in order to measure large amount of voltage or current, we need to convert the galvanometer into either ammeter or voltmeter. So during the conversion of ammeter, we connect a resistance which is very low with parallel to the galvanometer. So the overall combination will act as an ammeter. However, in case of voltmeter, the situation is different. For galvanometer, for ammeter is a low resistance galvanometer, but for voltmeter is a high resistance galvanometer. So in order to make the galvanometer voltmeter, what we do, uh, as we had discussed in the previous class, in order to convert galvanometer to voltmeter, suppose this is a galvanometer. When we connect a resistance which is high, if suppose this is the galvanometer, it has some resistance R and this is another resistance RS. So in case of voltmeter, when this combination will act as a voltmeter, when RS will be greater than R, and this combination, sorry. So this is the condition under which the galvanometer acts as a voltmeter. So this is the overall idea about the conversion of galvanometer into voltmeter. Now let's solve a question. And the question says a galvanometer coil of 40 ohm resistance shows full range deflection for a current of 4 milliampere. How can this galvanometer be converted into a voltmeter of range 0 to 12 volt? So what's given in the question? In the question it is given that the galvanometer has a resistance of 40 ohm. So if you see there are two resistances here in this case. So one is resistance of the galvanometer and another is the resistance which will be connected in series with the galvanometer to convert it into voltmeter. So in the question it is given the galvanometer has resistance of 40 ohm and it shows full range deflection for a current of 4 milliampere. So the current which is passing through the galvanometer is 4 milliampere. Now how this galvanometer can be converted into a voltmeter of range 0 to 12 volt. So if we want to convert the galvanometer into a voltmeter with range of 0 to 12 volt, that is total voltage passing through the total voltage across the voltmeter will be 12 volt. Then what we need to do, or how we need to modify the galvanometer circuit so that it will act as a voltmeter of range 12 volt, where the galvanometer coil has resistance 40 ohm and the deflection is maximum for a current of 4 milliampere. So I am giving you a few minutes to solve this question. Please try yourself because this is a very simple circuit. You just need to apply current in the circuit and measure the voltage across the circuit. And you from this arrangement, you need to find, since you know voltage, you know current, and you know the resistance of the galvanometer. So you need to find this RS. That is, what is the resistance value of the series resistance RS, so that the overall combination will be acting as a voltmeter of range 12 volt. So uh, please try this question. After that, we will discuss. So can all of you access the chat box in the Teams? Like this, in this meeting, there is a chat box in the Teams. So can all of you access the chat box so that we can discuss the answers? Like you can solve the answer and post that in the chat box so that I can see what's the answer. Anyone? Can you access the chat box in the Teams? So let's start solving this question. Now the value we know, the resistance of the galvanometer. So if you see the circuit, there are two resistances. One is of galvanometer. So this is a galvanometer G connected, and we need to connect a resistance in series to make the combination a voltmeter. So this is 40 ohm. It is given in the question, and this is a resistance R. We need to connect in series so that this total will act as a voltmeter. So this will act as a voltmeter with range 0 to 12 volts. So total voltage will be 12. Now also one more information given that the current is 4 ampere. So the current is 4 milliampere. So 4 milliampere current is flowing in the circuit. So as all of you know, if there is a series circuit, the current remains same, but the voltage changes. Like if this is the total combination, then some voltage will drop across this resistance, that is the galvanometer of 40 ohm, and some resistance and some voltage will drop across the resistance, series resistance capital R. So if you apply Kirchhoff's voltage law, then total voltage drop will be V is equals to I into total resistance. Now here, as you can see, there are two resistance connected in series. Can anyone tell me if the resistance are connected in series, then what will be the equivalent resistance of the two resistances? Anyone? So
Sir,
if,
chat box coming, sir.
sorry,
Chat box didn't work, sir. Chat box option
okay,
didn't, sir.
okay, it's okay. So you can, if you have any doubt, you can add on mute and ask me.
Okay,
So,
sir.
can you tell me? Can anyone tell me what will be the equivalent resistance if one resistance is R and another resistance is 40 ohm and both are connected in series? Then what will be the equivalent resistance?
40 plus R.
Yes, so the total resistance will be 40 plus R. So when you apply this, when you put the value of R here, total R, then we can find the, so this voltage we know 12 and the current is how much? Current is 4 milliampere. So current is, suppose we can write I, then it will be how much? It will be R plus 40. So 12 will be IR plus 40I. Then R will be how much? Then R will be 12 minus it will be 12 minus 40I divided by, so 12 minus 40I will be IR. So R will be 12 minus 40I divided by I. So simply direct we can say that it will be 12 by I minus 40. So what is the value of I? Current is here 1 milliampere. So it will be 4 into 10 to the power minus 3 ampere minus 40. So it will be 4 divided by 12 is 3. So it will be 3000 minus 40. 3000 minus 40, which will be equal to 2960 ohm. So this is the value of the resistance. This is the resistance value. If we connect this resistance in series with the galvanometer of resistance 40 ohm, then for a current of 4 milliampere, we can find the voltage. We can find the voltage by converting it into a voltmeter, and it will measure voltage. So what we did here, so in the question it was given that the galvanometer coil has resistance of 40 ohm and the current passing through is 40 milliampere. We know 4 milliampere, and we know galvanometer is generally used to measure small current or small voltage, but when we need to convert it to ammeter and voltmeter, so we can measure higher current or voltage. So you must be remembering that when we are converting the galvanometer to ammeter, we are connecting a resistance in parallel. So there, since the resistance was very small, so the current, most of the current was flowing through that resistance, and it was bypassing the current, and only small current, because galvanometer is generally used for small measurements, so only small current was flowing through the galvanometer, and according to the resistance we are connecting, we can change the range. Similarly here, so the range of the voltage that the voltmeter can measure will depend upon the value of resistance we are connecting in series, because as you can see, if the total voltage is 12 volt, so can anyone tell me, if the total voltage is 12 volt, then how much of voltage will drop across the resistance and how much voltage will drop across the galvanometer? Can anyone tell me? What will be the voltage across this and what will be the voltage across this? The total voltage is 12. Can anyone tell me? Total voltage is 12. So voltage drop across the galvanometer and voltage drop across the resistance will be the total voltage drop across resistance and capacitor will be 12 volt. So can anyone tell me what will the voltage drop across the galvanometer and what will the voltage drop across the resistance? So if you see here, we know V is equals to IR, V equals to I into R. So the voltage drop across the galvanometer will be 4 into 10 to the power minus 3 into R. R is 40. So it will be how much? It will be 160 into 10 to the power minus 3, or 16 into 10 to the power minus 2. Or simply you can write it as 160 millivolt. So as you can see, most of the voltage is dropping across the resistance R, because only 160 millivolt of voltage is dropping across the, only 160 millivolt is dropping across the galvanometer. However, all the remaining voltage, so the remaining voltage across the resistance will be how much? It will be 12,000 millivolt minus 160 millivolt. So you can clearly see it will be 11,840 millivolt, or 11.84 millivolt. So you can see most of the voltage dropping across the resistance which is connected in series. So like in case of ammeter, so the resistance which we are using in parallel was used to bypass most of the current. So similarly, in case of a voltmeter, the resistance which is used in series, the main function of the resistance is to drop all the sources. Most of the voltage will be dropping across that resistance, and only small voltage will be dropping across the galvanometer. So this is the correct answer. So if we connect a 2900 or 2.96 kilo ohm of resistance in series with a galvanometer, then the equivalent circuit will act as a voltmeter and it will be having range of 12 volt. So is there any doubt in this question? Anyone? So we are good to go to the next question. So next we studied in week 2 and week 3, we studied different electrical components like resistors, capacitors, inductors, and different wire family. So as you can see, this is the symbol of resistance, this is the symbol of capacitor, and this is the symbol of inductor. Capacitor contains two parallel plates and it has some dielectric in between. So let's discuss each of the electrical components in details. So now coming to resistor, generally, as you can see, this is the, you must have seen, this is a resistor, and also the resistor has some resistances also, but with that resistance it has some wattage, like how like what will be the maximum power it can handle. So you must have seen small resistors, and also the for some resistors the size is quite large, so they are called as high wattage resistors. So most of the resistors you see, they're mainly up half watt or quarter watt. However, for high current operations, in V is equals to IR, or power is also direct proportional to I. So for high current measurements, we use higher wattage of resistors. So if you see a resistor, you must have seen there are different color codings in a resistor. So there are registers where there are 4 bands, and also there are registers where there are 3 bands. So here you can see in this resistance there are four bands, 1, 2, 3, and 4. But here in this register there are 5 color bands, 1, 2, 3, 4, 5. So we using these color combinations we can directly calculate the resistances. So how to calculate the resistance? By seeing the color bar. This is the color and their corresponding digits, like black stands for 0, brown for 1, red for 2, orange for 3, like that, white for 9. So these are the colors and their corresponding numbers. So how to calculate the resistance? Suppose suppose you take an example. This is a resistance, and we want to calculate the this is the resistor, and we want to calculate the resistance. So you can see the first color is brown, second it is red, third color is brown again, and this is tolerance. So now here it is clear. So suppose this is gold, it is looking like yellow, but suppose this is gold, and this is brown, this is red, and this is again brown. So what is the method of calculating the resistance? So if we calculate the resistance, then corresponding to this first color number, it will be first digit. So it will be first digit. Then for second number, it will be second digit. There will be another digit here corresponding to the second number. And the third band, that is the band C, is multiplier. So we will multiply 10 to the power that number. Suppose this is brown, and for brown it is 1. So 10 to the power 1 will be multiplied, that is 10 will be multiplied. And then this fourth band is called as tolerance, and this says the variation in resistance. That suppose the band is gold, so there will be plus minus 5% variation in the resistance. So if you compare the color codes, the first one is brown, so here brown is 1, so the first number will be 1, first digit. Then second digit is red, so second digit red means it is 12, so 1 and it is 2, so total 12. Third is multiplier C, C is again brown, so if you multiply brown means 1, so 10 to the power 1 is 10, so it will be 12 into 10. So it will be 120 ohm. And since the tolerance in the fourth band is gold, so the tolerance will be plus minus 5%, plus minus 5%. So the resistance may vary from 114 to 126 ohm. So this is the method to calculate the resistance. Then now consider the resistance which have more than 3, that more than 5 more. So there are 5 color codes. So like this example you have tried, this is the same thing, brown, red, brown, and gold, and you can see this is 120 ohm and 5% is the tolerance. And simply if you can calculate it, so this is yellow actually. So as you can see, yellow here stands for 4. So the first here, in case of 5 bands, there will be first, second, third digit, and then there will be multiplier. So here black will be third, violet will be second, and first will be yellow. So yellow is 4. Then second is violet, so violet is 7. Second digit is 7. Third digit is black again, so black is 0. So it is 470. Then the multiplier is brown, so 470 into 10. For brown, it is 10 to the power 1 or 10, so 10. So it will be how much? It will be 4700, so it will be 4.7K. And since the last is tolerance and tolerance for brown is 1%, so it will be 4.7 plus minus 1%. So this is the resistance of the resistor. So is there any doubt how to calculate the resistance by seeing the color codes printed on the resistors? Yes. So now let's solve a few questions regarding this. So now in the figure you can see there are 5 resistors. So and there are different color codes. So you don't get confused with the colors. This is yellow, this is violet, this is orange, and this is gold. This is gold, red, red, red. Then next is gold, brown, black, and then brown. Then fourth one is brown, green, red, and gold. The last one is yellow, violet, black, and gold. So these are 5 resistors. So please calculate the resistances and we will discuss in details what will be the resistances for each resistor. So I am giving you 3 or 4 minutes. So please calculate and tell me what will be the value of resistances for each resistors. Anyone calculated the resistance values? Anyone? So this first one is yellow, violet, brown, gold. This is gold, red, red, red. Brown, black, brown, brown, green, red, gold, yellow, violet, black, gold. So calculating the resistance of this first resistor, what we have? This is yellow, violet. This is not brown, this is orange. Yellow, violet. For yellow, what is the number? Yellow is 4. This is first digit will be 4. Then violet, for violet is 7. So it is 7. Then orange, for orange, the multiplier 10 to the power 3. So 47 into 10 to the power 3. So it is 47 kilo ohm. And since the fourth band is gold, so the tolerance will be 5%. It will be plus minus 5%. Similarly, for this resistance, the gold, for gold, the value is I think so. If you see, I think these are inverted. So gold will be fourth band. So you will start from this is 1, this is 2, this is 3, and this is fourth band. So red, 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 and gold. So red is 2 and gold is 5%. So red will be 2. Second is red 2. Then 10 to the power 2 for red. So it will be 2200. So it will be 2.2 kilo ohm plus minus 5%. Similarly, for this, it is brown, black, brown. And for brown, we have 1. And for black, we have 0. So for brown, it is 1, black 0. And again, for brown, it will be 10 to the power 1. So it will be 10 into 10, that is 100 ohm. And tolerance will be gold again, so plus minus 5%. So don't get confused. I think these are inverted. So for this is 1. Let me try in a different color. So suppose I am writing it with this. So this is 1, this is 2, this is 3, and this is 4. Similarly here, this is 1, this is 2, this is 3, this is 4. So but here the orders are correct. So you need to identify which is the first band and which is the last band. And then you can verify it by measuring with the help of a multimeter. So again, calculate. So for brown, it is 1. So brown is 1. Green is 5. So green is 5. And red is 2. So it will be 10 to the power 2. It will be 1500, that is 1.5 kilo ohm plus minus, again plus minus 5% the tolerance. Now the last one is yellow. So first is yellow, so yellow means 4, and violet stands for 7. Then black is 0, so it will be 10 to the power 0, 10 to the power 0. So it will be only 47 ohm, plus minus tolerance is 5%. So these are the 5 resistors and these are their resistances. So in this way, we by seeing the color codes of each resistance, we can calculate what are the resistance values. So is there any doubt with this process? Can all of you calculate? Next, if you see a resistor, you can easily calculate the resistance. And to verify the resistance, you can measure the resistance by a multimeter. So is there any doubt, or we should proceed to our next component, that is capacitor? Yes. Next, we know there are capacitors. Capacitors are very popular. They are used in many different applications. So generally, what is a capacitor? A capacitor is a generally the capacitors are parallel plate capacitors. And in case of parallel, there are 2 conductors. This is 1, this is 2. It is charged positively, and this is grounded. So since this is grounded, so there will be an induced charge. So similar amount of negative charge will be induced here, and there in between the 2 plates there is a dielectric, and the dielectric is used to enhance the electric field between the 2 plates. And we know in case of if these are 2 parallel plates and both have charge sigma, then if this is sigma, then in this side it will be sigma by 2 epsilon 0, and in this side it will be sigma by 2 epsilon 0. Since there are 2 oppositely charged, so for one it will be plus sigma, and for one it will be minus sigma. So what will be the total in between 2 plates? For this plus sigma, it will be sigma by 2 epsilon 0 on the right side, and for minus sigma on the left side, it will be again sigma by 2 epsilon 0. So the total resistance will be sigma by epsilon 0, and this is the total electric field. So the total electric field due to the charge density sigma on the 2 plates, and when the 2 charges are equal and opposite, then the electric field induced will be sigma by epsilon 0. So between the 2 plates, the lines of force will be like this. The lines of force. So if you see, you must have seen this is the capacitor and these are 2 terminals, and you can see here it is written, it is the, sorry, here it is written, it is the value of the capacitance. Capacitance is 2200 microfarad, and the operating voltage is 35 volts. So this can operate with a voltage of 35 volt, maximum voltage of 35 volt, and the capacitance value is 2200 microfarad. So if you discuss about the constructions, you can see this is basically constructed in this way. This is basically constructed in this way. This is a 1 plate, this is another plate, and there is a separator which is an insulating metal or dielectric. So when 2 opposite and equal to opposite charged but equal amount of charged plates are placed with with some distances, and again the within between the separation of the 2 plates we can keep either air, and also we can put any dielectric medium, and that dielectric constant plays an important role. And we know if the distance, if the suppose this is 1 plate and this is another plate, there are 2 plates, like, so if the area of the plate is A and the separation between the 2 plate is D, then the resistance, then the capacitance of this system is epsilon 0 A by D. Epsilon 0 A by D. So in order to increase the capacitance, we need to increase the surface area and we need to decrease the distance. So as you can see, so as we go on increase the area, so you have to use more larger strips. So the capacitance will be increasing. So if you see, in order to increase the capacity, the size will be much bigger because we are increasing larger area electric plates. So this is the basic capacitor, and also there is one more property of a capacitor. Since like resistance has some reactance which is called as resistance. Similarly, capacitor has some reactance that is called capacitive reactance, and it has the capacitive reactance which is known as Xc is called as 1 by omega c. So this is the capacitive reactance. So when the frequency of a signal passing through the capacitor varies, its resistance also varies. And if the frequency is 0, so capacitance is, so the reactance of the capacitor is infinite. So for a DC current, the capacitor acts as an open circuit. So capacitors are mainly used in AC signals. So let's solve a question regarding the capacitor. Now the question says, in a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 to the power minus 3 meter square, and the distance between the plates is 3 mm. Calculate the capacitance of the capacitor if it is connected to a 100-volt battery. Then what will be the charge on the each plate of capacitor? Again, what happens when a 3 mm mica sheet, which are dielectric constants of 6, is inserted between the plates? So in the question, what is given? In the question, it is given that it is a parallel plate capacitor. It is a parallel plate capacitor. So it contains two plates separated by some distance, and it has air between the plates. So the dielectric constant, we know the dielectric constant of air is 1. So epsilon r is 1 for air. So again, the area of each plate is 6 into 10 to the power minus 3 meter square. And the distance between the plate is 3 mm. So 3 mm is the distance between the two plates. Then we need to calculate the capacitance of the capacitor. When it is connected to a 100-volt battery, what will be the charge on each plate of the capacitor? So first we need to calculate the capacitance of the capacitor. And when it is connected to a 100-volt battery, so when we connect a 100-volt battery, then what will be the charge on each plate of the capacitor? Because there will be induced charges. So what will be the charge on each plate of the capacitor? That will also depend upon the value of the capacitance. So with this given information, we will calculate the value of the capacitance, and after that, after that question, it says what happens when a 3 mm mica sheet, which has dielectric constant of 6, is inserted between the plates. So when a dielectric constant of when a material having dielectric constant 6 is inserted between the two plates, then what will be the result? That is whether it will increase the capacitance or decrease the capacitance, we will see. So please calculate this question and tell me what will be the capacitance of the capacitor and what will be the induced charge of the capacitor when a 100-volt battery is connected. So please try this question, and after a few minutes we will discuss. So anyone calculated what will be the capacitance of the capacitor? It is very simple. This is the formula. Capacitance is epsilon 0 A by D. You know epsilon 0, you know A and you know D. You can directly calculate.
Capacitance is 17.7 picofarad.
Yes. And then what will be the induced charge?
1770 into 10 power minus 12 coulombs.
Yes. So good. Then what will be the case when a mica sheet is introduced between the two plates?
Circuit's capacitance will increasing by 6 times of the previous one.
Yes.
That is 106.2 picofarad.
Very good. So let's solve this question. So we know the formula of the capacitance is for a parallel plate capacitor, capacitance C is epsilon 0 A by D. And what is the value of epsilon 0? What is the epsilon 0? What this is called? What is the name of this symbol? It is absolute permittivity. So here the dielectric constant is also called the dielectric constant. So dielectric constant is epsilon 0 epsilon r. And if for epsilon r, for air epsilon r is 1, and for any other dielectric, yes, like here in the question it is mica sheet, it will be epsilon r will be 6. So we know the value of epsilon 0. The value of epsilon 0 is 8.85 into 10 to the power minus 12. 8.85 into 10 to the power minus 12 into area is 6 into 10 to the power minus 3. 6 into 10 to the power minus 3 divided by 3 into 10 to the power minus 3, because the distance between them 3 mm. And always remember, when you are calculating something, convert all the dimensions into a single unit. Like when you are calculating in meter, then all the quantities like area will be in meters and distance will be in meters also. So when you are converting millimeters into meters, so it will be 3 into 10 to the power minus 3 meters. So it will be how much? It will be 17.70 into 10 to the power minus 12. And what is the unit of capacitance? It is farad. So we know 10 to the minus 12 is pico. So it will be, suppose we assume it, so it will be 1800 picofarad. So this is the capacitance of the parallel plate capacitor. And when it is connected to a 100-volt battery, we know Q equals to CV. Charge induced will be capacitance into voltage. So induced charge will be how much? 18 into 10 to the power minus 12 into 100. So it will be how much? It will be 18 into 10 to the power minus 10 coulomb. Or if you try to do it, it will be 1.8 10 to the power minus 9 coulomb. So 1.8 nanocoulomb charge will be induced, and since it is positive, it is negative, there will be 1.8 coulomb charge, 8 nanocoulomb charge here, and negative 1.8 nanocoulomb charge induced here. Now what happens when a 3 mm mica sheet is inserted? So we know here it is epsilon 0 A by D. So when it is mica sheet is present, so the new capacitance will be epsilon 0 epsilon R A by D. So since epsilon R is 6 here, so the capacitance will be 6 times. So new capacitance will be 6 into old capacitance. So it will be how much? 108 picofarad. Similarly, if you are calculating the induced charge, then the charge induced will again be how much? 108 into 10 to the power minus 10 or 1.08 into 10 to the power minus 8 coulomb. So this is the total calculation. So this is the value of the new resistance, new capacitance, sorry, and this is the value of the old capacitance. And the old capacitance value is 1800 picofarad, 18 picofarad, and the new capacitance value is 108 picofarad. And since the charge is Q equals to capacitance into voltage, so induced charge will be 1.8 × 10⁻⁹ coulomb. And in case of the new capacitance, so new capacitor where the air is replaced with the help of mica sheet, since mica sheet has dielectric constant of 6, then the capacitance will be increased 6 times. And similarly, the induced charge will be also increased 6 times. So this is the induced charge. So is there any doubt in this question? Anyone? Any doubt?
What is the effect of the thickness or length of the mica sheet?
Sorry?
What is the influence of the length or a 3 mm mica sheet?
Actually, in case of a dielectric, what they do, dielectrics are the substances which are insulators, that is, they don't conduct electricity, but they only transfer the effect. So there are different dielectrics, like actually here what happens in case of capacitor, there are no free charges. There are no free charges because since here there is, in between there is air. Suppose, let me add another slide and explain. What happens? There are, suppose this one is, if this one is grounded and we give it plus sigma charge, so this, since it is grounded, so there will be induction of minus charge. So what happens here? Both the plates have similar or same amount of charge, but the charge are different. So it is positive and it is negative. And here we are placing some dielectric material. Suppose it is air or any mica sheet. So in case of air basically, in case of air consists of mostly oxygen and hydrogen and nitrogen also. Sorry, oxygen, nitrogen, and nitrogen, and both of them are homonuclear molecules. So if you see in case of H2, since there are 2 hydrogens, so their center of positive charge and center of negative charge both coincide at a single point. So they don't have any permanent dipole moment. But here, when we are applying mica sheet, since mica sheet, this is the mica sheet. In the mica sheet, the material is such that it will be having an induced dipole moment. So suppose this is plus, then suppose this is plus and this is minus. Then minus will be here, plus will be here, minus will be here, plus will be here, like that. So here there are more induced charges. So since you see Q equals to CV, so since suppose for a constant voltage, for a constant capacitance, Q is direct proportional to C, and for a constant voltage, C direct proportional to Q. So here Q is not free charge, it is bound charges that are on the surface. So here, as you can see, in case of when we are replacing air with mica sheet, there will be more induced charges. So the effect of the mica sheet will be to enhance the capacitance. That's why the capacitance will be increased. And this is the what we can say. This is the main reason why we induce different types of insulators or different type of dielectric materials. And also if you see epsilon 0, what is the actual formula for epsilon r? Because epsilon is equal to epsilon 0 into epsilon r. So what is epsilon r? It is relative permittivity of the medium, and relative permittivity of the medium is what? It is the ratio of the force between two charges when they are placed in that medium, and the force between the same two charges at same distance when they are placed in air. So why? So it is that medium. Suppose we are calculating for mica, then it will be force between the same two charges in mica medium, and it will be in air medium or free space medium. So also you can see, since the dielectric constant is 6, so the force is again increasing. So that is the electric force, and so similarly, since force is related to the charge, so the induced charge are more, because we know F is equals to QE. So F that proportional to Q. So also your charge are induced. So when Q is increased, the total force will be increasing. And so this is the definition of the dielectric constant, that the force between the two charges under same condition, it is enhanced, and also due to that the capacitance is enhanced. So now it is clear.
Yes, sir. So one more question.
Yes.
Sir, what will be the capacitance if the dielectric is placed within the dielectric is placed partially placed basically within the plates of the capacitor?
Yes. Then we can again calculate, like suppose we are placing a dielectric here. Suppose there are suppose this is the plates. The plate has area A, this has area A, but the distance between the two is D, but the dielectric is placed within a distance of D by 2. Suppose this is only D by 2, and this is what? This is air. So we will calculate for air. There will be contribution for air, and there will be contribution for this dielectric. So there will be two. One will be C air, and another will be C dielectric, and they are both lying in between the two plates, since the air and both dielectric is lying. So here it will be C air will be epsilon 0 A, because A is same for both the cases, because here the dielectric is throughout the area, but there will be one case where the dielectric is not throughout the area, it is half of some area, like dielectric is placed here only. Then the effective area will be again changed, but here the D will be changing to D effective. And again it will be epsilon 0 epsilon r A by D effective. So what happens here? Epsilon 0 A by here D effective almost, since D by 2 here, so this will be D by 2, this will be D by 2. So it will be D by 2 plus epsilon 0 epsilon r A by D by 2. So it will be 2 epsilon 0 A by D plus 2 epsilon 0 epsilon r A by D. So this will be the overall capacitance when it is partially filled with the capacitor. And also there are other one different question that you can also go think of, like the capacitor. Initially there was total plate, then we slided it to some portion, then what will be the amount of work done, or like that, there then we can also calculate that case also. So similarly what we can do, we will calculate capacitance. From the capacitance we can calculate the voltage, and from that voltage we will calculate work done, because we know potential or voltage is electric potential, and potential nothing but work done per unit charge. So from that also we can calculate. Is it clear to you?
Yes, sir.
Okay, so let's solve another question. So I always encourage you to ask your doubts, so it will be better. I can also try to explain you in a better way. And also, since this is an interaction session, so the main aim of this session is to interact with you if you have any doubts in your discussion. So then this is the question. So this is a very good question actually. What is the current passing through the 10 ohm resistance in the given circuit when the key K is closed? So the question says, what is the current passing through the 10 ohm resistance in the given circuit when the key K is closed? So what we will do here, as you can see here, since the key is open and it is a 3-volt power supply, and here the key is open. So now we will close the key. So we connected the key. Then what will happen? Then current will be flowing in the circuit. Then some current will be going here, some current will be going here. Then it will be again coming here. So here we want to calculate what will be the amount of current that will be passing through the 10 ohm resistance. So suppose this is I inductor or IL and this is IR. Then what we need to find? We want to find what is the value of resistance, what is the value of current which will be passing through the 10 ohm resistance. So please try this question. Then after a few minutes, if you can do it, then it's okay. Then we'll discuss it. So anyone tried to solve the question? Yes.
So 3/40.
3/40. No, the answer is wrong. I think yes, it is wrong. So please rectify and try to. Actually, the since as you can see here, there is one inductor of one end is connected, and there is another resistance which is connected in parallel to that inductor. So there is a trick. So please try to think what will be the case here. Okay, let's solve this question. Now what it says, what is the current passing through 10 ohm resistance in the given circuit when the key K is closed? So what is the value of the voltage here? Voltage is 3 volt. The value of voltage here is 3 volt. And one resistance is 10 ohm here, another resistance is 1 Henry. So as you know, since this is 3 volt and there will be current, there will be some current and there will be equivalent resistance. But here it is saying when the K key is closed. So when the key is closed, this is a what type of power supply? AC or DC? This is a DC power supply and this is DC voltage of 3 volt. And we know like there is a reactance of inductor also, which is known as inductive reactance, and that is known as XL is equals to omega L. Since omega is 0 here, so 0 into L is 1 Henry, so it will be 0 ohm. So what basically XL has two components, like XL generally we write it as R plus. So it has two components, R plus JX. Like the total reactance has some real part and some imaginary, that is different. We'll discuss it later. But here you see, since the frequency is 0, since it is a DC volt, the resistance of this inductor is 0. That is, there will be no resistance here. So there will be simply OR. So what will the replace circuit here? So when the key is closed, then this is 10 ohm and then this will be simple, this short circuit. So the inductor will be getting converted to short circuit. Like in case of capacitor, the capacitor has infinite resistance for a direct current. So when there is a direct current, then the capacitor will act as open circuit and resistance will be infinite. But here, since there is an inductor and inductor offers no resistance to DC current, so there will be zero resistance. So this is the case. So as you can see, this is resistance 10 ohm and this is 0 ohm. So since there is no resistance in the path, like current I is coming here and some current is going here IR and some current is going here IL. Since IR is 10 and IL is 0, so all the current will be flowing through that zero resistance path, because we always know current always follows the least resistance path or low resistance path. And also there is a division rule. Like suppose this is resistance R and this is resistance R. So suppose this is I, and across both the resistances, this is R1 and this is R2, and voltage V is dropping across. Since both resistance are connected in parallel here, voltage drop will be equal in both the cases. Here V2 and here V1 both will be equal. V2 will be V1. So when you compare, what will be the voltage? Voltage will be I into V is equals to IR. V is equals to I into R. Then we want to calculate what will be the value of. Let me add another slide here. So basically what happens? We know V equals to I R. So R will be R equivalent, and R equivalent is how much? R equivalent is, we know for parallel combination, the resistance, the equivalent resistance will be 1 plus R1 by 1 plus R2. So it will be how much? R1 R2 by R1 plus R2, R equivalent. So it will be I into R1 R2 by R1 plus R2. Since the voltage, so this is the voltage, then what is the current? Suppose current I1 is flowing across R1 and current I2 is flowing across R2. Then we know V is equals to IR. So I is equals to V by R. So V by R1, it will be how much? I is equal to R1. Since V is equals to I into R1 R2 by R1 plus R2, so it will be I into R1 R2 divided by R1 plus R2 into 1 by R1. So R1 gets cancelled out. It will be I into R2 divided by R1 plus R2. Similarly, what will the current I2? I2 will be I into R1 divided by R1 plus R2. So if there are two branches, the current flowing through each branch will depend upon the resistance on the other branch. Like it is the total resistance R1 plus R2. So similarly, in this case, you can see one resistance R1 is 0 and R2 is 10. So when you calculate R1 is 0 and R2 is 10, then what will be I1? Then I1 will be how much? Since it is R2, it will be not equal to 0, but since R1 is equal to 0, so it will be 0. So here in this case, no current will flow through this resistance 10 ohm and all the current will be flowing through this inductor path because it is short circuited. So here the current flowing through resistance will be how much? 0. So IR 10 ohm will be 0. No current will flow across the resistance. Is it clear? Yes. Everybody understood why there will be no current in the path of the inductor when the key is closed, because it is very important concept. And also the current and voltage division rules that are also very important, because here if there are two circuits and they have the resistances R1 and R2 are connected in parallel, then in that case there will be division of current, because when there is a parallel circuit the voltage remains same across each branch but current differs. Like in series the current remains same but voltage across each component is different. So using that relation, that is basically Kirchhoff's law, and using that we can easily calculate the current and voltage flowing. So this is the equivalent current that will be flowing across, all the current will be flowing across the upper path like 0 ohm path or the path in which inductor is connected, and there will be no current in the 10 ohm resistance. So now let's discuss next question. Now the question says a cylindrical conductor of length 0.5 meter and cross-sectional area 0.01 meter square. Then the resistivity of the material is 2 into 10 to the power minus 8 ohm into meter. Then find the resistance of the material. So we know resistance, how the resistance appears, because when in a material current flows, then due to the collision between the electrons, there is some resistance to the flow of current, and that act as a oppose or barrier, and that gives rise to resistance. So if you compare, suppose this is a wire, this is the cross-sectional area A, and this is the length of the wire L. So since there are collisions, since there are suppose there are electrons that are flowing, like that the electrons are flowing. So we need to calculate the resistance. So how will resistance vary? So as you can see, this is the area cross section. So area cross section, this is the A. So across this area there will be electrons. And since the electrons are flowing from this to this side to this side, if the length will be increasing, that is the electron will be needing, so the electron will be passing through a longer path, and so in passing through a longer path, they will collide more frequently. So due to more collisions, the resistance will be increasing. So the resistance is directly proportional to the length of the wire. And similarly, if the area is A, as you can see, if the area is bigger and bigger, then there will be less collisions because they will be having more space to travel. Like this is a small area and there are 3 electrons are flowing. So they will collide with each other more times. But if there is a large area and 3 electrons are flowing, then the probability of collision between them will be decreased. So the resistance is inversely proportional to the area cross section. So resistance is directly proportional to L by A, and so there is a proportionality constant here, which is rho L by A, and this rho is known as resistivity. So this is the property of each material. So there are some complicated things you will be studying it for how the resistivity varies, what is the resistivity, how resistivity varies temperature. These are different things. So this is the relation between resistance and resistivity. So when we want to calculate the resistance of the material, then you have the values of length. Length is 0.5 meter. Let me add another slide. R equals to rho into L by A. You have the value of rho, you have the value of A, and you have the value of L. The value of rho is how much? 2 into 10 to the power minus 8 ohm into meter. So 2 into 10 to the power minus 8. The value of A is 0.01 meter square. 0.01 meter square. It is ohm into meter. And length is 0.5 meter. So this length is 0.5 meter. So when you put all the values, you can easily find the resistance. It will be coming in ohm because this meter, and this meter square will get cancelled out. So the resistance will be coming in ohm. So this is a very simple question, and using this formula, we can easily calculate. Now, I think there will be no doubt in this question. So let's go to our next question, our next component. So there are mainly three components: resistors, capacitors, and inductors. So we discussed about resistors and capacitors, and now let's discuss about inductors. So basically, inductors consist of a large number of turns of wires, like you can see here, and the wires are wounded over a core. This is a cylindrical core. So this core may be air, or this core may be argon, or many other materials, and these are used to hold magnetic field lines, because you can see if in case of an inductor, the magnetic field lines are like this. So the field lines, so the magnetic field lines are like this. So there are different types of symbols corresponding to the cores. So this is air core, there are no but in case of iron core, we use two lines here. And in case of ferrite core, like here you can see, suppose this is a ferrite material. Here you can see, suppose the material is ferrite. Ferrite is a ferromagnetic material. So ferrite core is, it is given in this dotted line. And when there is a variable core inductor, then the arrow mark is used. So this is a inductor, and also if you consider about inductor, if you consider different components, this is the resistor, and it has a symbol inductor and capacitor. And the current, if the resistance is R, then current is given by I is equal to V by R, and voltage is V equals to IR. But here in case of inductor, the current is given by integration of voltage into divided by the inductance, and voltage is L di by dt. Similarly here, the current is C dV by dt. So these are due to the response of the components, that is inductors or capacitors. The current and voltage changes like that. So we will be discussing it in details when we will be talking about RC circuit and RL circuits. Then in there we will be discussing, because in there these plays significant roles, because when we consider about AC circuits, when there is function of frequency, that is, then there will be derivative of time, then there with respect to time, the voltage and current will be changing, and with that, the significance of these components increases. Now, if we are talking about inductor has a property which is called as self-inductance, and due to the self-inductance, if the magnetic flux linked with the coil changes, then an EMF is induced in the coil, and this is the property of the inductor, and this property is known as self-inductance. And the coil capacity, and this basically reflects the capacity of the coil to provide current. And we know the magnetic flux direct proportional to I is equal to N I A, somewhere like that is the relation. So phi direct proportional to I. So there is a constant, dielectric constant L. So L equals to phi by I. So if there are number of terms N, then self-inductance will be and n phi into I, and the unit is Henry. The unit of the self-inductance is Henry, also mutual inductance is also Henry. And if you talk about electromagnetic induction, then we know EMF is directly proportional to rate of change of EMF is directly proportional to rate of change of magnetic flux. So from that relation, we can easily calculate this L is equals to minus E di by dt, because when we apply the formula E is equals to minus N d phi by dt, then in place of phi we can directly put phi is equals to Li, so it will be L into di by dt. Then from this we can directly calculate L is equal to minus E divided by di by dt. So when there is change in current, there will be induced in EMF. So this is self-inductance. And similarly, if there are two inductors, then there will be mutual inductance. So due to so what is mutual inductance? Now, due to the property of mutual inductance, the change in current in one coil will induce EMF in another coil. Like here you can see, here current I1 is changing, and due to that current I1 is changing, the flux linked with this coil 1 is changing. Since the magnetic lines of force are passing through this coil also, so the flux linked with this coil is also changing, and due to this, the EMF is induced in the second coil. So this is the relation for mutual inductance. That is mutual inductance of second with respect to 1. 1 means of 2 with respect to 1. And this is the relation. Similarly, if you do the same calculation like electromagnetic formula in law of electromagnetic induction, then you can find the mutual inductance is directly proportional to the EMF induced in 2 and inverse proportional to rate of change of current passing through this coil. So this is the two concept of mutual inductance and self-inductance, and both the unit of mutual inductance and self-inductance is Henry. And also there is another unit which is called as Av Henry, and 1 Henry is equal to how much? 10 to the power 8 Av Henry, because this is SI unit and this is electromagnetic unit. So now let's solve a few problems regarding this self-inductance and mutual inductance. Now the question says, when a current of 2 milliampere is applied to a coil with 100 turns, then a magnetic flux of magnitude 0.2 Weber is linked with it. Find the self-inductance of this coil. So the question is very simple. We know the formula for self-inductance. L is how much? L is N phi by I, and here N is given. N is how much? N is 100, and phi is given because magnitude, the magnetic flux of magnitude 0.2 Weber. So phi is how much? 0.2, and also the unit of flux is Weber, and also another unit is Maxwell. So here it is in Weber it is given, so we don't need to change it. And then current I, and also I is also given. I is 2 milliampere. So when you calculate, it will be 100 into 0.2 by 2 into 10 to the power minus 3. So it will be 10 Henry. So the self-inductance of the coil is 10 Henry. And in the question, it was given that the current is 2 milliampere, coil has 100 turns, and the flux of magnitude 0.2 Weber is changing. So this is a very simple question. So this is the value of self-inductance of the coil from the given questions. Now another question, another question, and this question says, when a current of 4 ampere between two coils changes to 12 ampere in 0.5 second in primary and induces an EMF of 50 millivolt in the secondary, then calculate the mutual inductance between the two coils. So this is the concept of mutual inductance. The problem is based on the concept of mutual inductance. And here you can see between in a time period of 0.5 second, the current is changing from 4 to 12. So there is a change in current and with respect to time. So we'll apply the second formula, that is this formula. We'll apply this formula. The first problem was this formula, but the second problem we'll apply this formula, and the formula gives EMF divided by di by dt. So we'll use this formula to calculate. So please use that formula and put all the values are given. It is a very simple question. So please put all the values and calculate what will be the value of mutual inductance. Please tell me what will be the value of mutual inductance. I will be giving you a few minutes. So please solve this. This is basically simple calculation. You know the formula, that put the values and find out what is the mutual inductance of the coil.
The 3.13 millihenry.
Yes. So if you calculate, then it will be how much m will be. So here one negative sign is there, you can see, and this negative sign is due to the Lenz's law. That is, the induced magnetic field will, the magnetic field which is induced will try to reduce the induced EMF. So the negative sign is coming like that. Suppose now let's calculate, and then after that we'll discuss about that. So when you calculate, it will be E2 divided by d I1 by dt. So E2 is 50 millivolt. So 50 into 10 to the power minus 3. And di by dt, as you can see, in a time period of 0.5 second, the change is 4 ampere to 12 ampere. So change is 8 ampere in how many time? 0.5 second. So it will be 50 into 10 to the power minus 3 divided by how much? 16. So it is 3.125 millihenry. So what is Lenz's law? I was saying Lenz law. So Lenz law is what? Suppose this is a coil and current is flowing through that coil. So the due to that current, the magnetic field will be induced so that it will tend to oppose the magnetic field that is already there. So if you see, you know, if this is a coil, then there is a magnetic field here. So suppose the current is flowing in this direction, like this is a current I. Then according to the Biot-Savart law and also the right hand rule, we can see, since the current is in this direction, the magnetic line supports will be like that, in this direction, passing through the plane of copper. So suppose if you there is a coil and it is placed inside a magnetic field, and this is the face of coil. Suppose this is the face of coil, and the current is flowing like that in this direction. Suppose the current is flowing in this way, so it will act as a north pole. The face of the coil which is facing towards us will act as a north pole. Like if the current is in anti-clockwise direction, then the phase of coil will be north pole. And if the current is in clockwise direction, like current is flowing in this direction, then it will be south pole. So it will be south pole, the phase of the coil. So this is basically so during the experiments, when in the upcoming weeks there will be experiment, then we will discuss about these phenomena in more details. So now let's come to the next section or next apparatus is called as cathode oscilloscope. And this cathode oscilloscope is used to measure voltage, current, and different waveforms. And if you consider about different components of cathode oscilloscope, so it has cathode ray tube. Cathode ray tube, basically this is the display of the cathode ray tube, and one electron gun assembly. And because the basically when there are spots like that. If you are measuring voltage, then there are spots, and these spots are due to the electrons are getting collided on the fluorescent screen. So the electron gun assembly there with the electron gun assembly is there inside the cathode oscilloscope, which produces beam of electrons, and there are deflecting plates, and the deflecting plates are used to deflect the electrons, so that we are getting somewhat here we are getting, somewhere here we are getting. So in throughout the screen we can get the spots by deflecting. Then there's fluorescent screen. This is the fluorescent screen where we see the signal, and there is a glass envelope. Why there is a glass envelope? Because as you can see, there are electrons flowing, and when the electrons get collided, then they lose their energies, and due to the low energy, they can't reach the screen. So we'll be discussing in more details about this. So let's first discuss about the main component, that is cathode ray tube. So this is the cathode ray tube, which is used in a cathode oscilloscope. And as you can see, this portion, this portion, this is the total portion, and this is glass tube. This is glass tube, and there is vacuum inside. As you can see, there is vacuum inside. So why there need of glass tube? Because we need vacuum inside this glass tube. So the whole assembly is enclosed inside a glass tube. So now let's see how the cathode tube operates. So it has different components. The first, there is a heating filament and there is a cathode. So this cylindrical this gray colored portion is cathode. And when the filament heats, when we supply high current in the filament, then the cathode is heated due to the filament, and since a cathode, so it will eject electrons and it will produce electrons. So the cathode materials basically are those materials are used who can easily produce electrons. So when an electron is fast produced, then electrons are focused with the help of focusing and accelerating anodes. So first there is this is a focusing anode, this is accelerating anode, this is a focusing anode, this is accelerating anode. But here there is a grid. This is a grid, and this grid is biased negative potential, and by varying this biasing we can change the brightness. Because suppose these are electrons and they are passing, this is the cathode. From cathode these electrons get emitted, and there is a grid. So since this grid is negative, grid has negative potential, so only those electrons which have sufficient energy, they can only pass through the grid. So since the grid is negative, so by changing the biasing potential of the grid, we can control the number of electrons that are passing through the grid, and they are being collided at this fluorescent screen, and they are making some spots. So since the intensity depends upon the number of electrons hitting the screen or fluorescent screen, so basically this grid is used to control the brightness of the screen. And again, there is a focusing anode, and they are focusing anode and accelerating anodes, because there are hollow anodes. So and there are biased positively. So electrons will get attracted and they are getting accelerated here. So they are mainly used to, since as you can see the electrons are coming here, but since there is a positive potential throughout this here, and again there is another positive high potential here. The electron will pass through this and they will get focused. And after the electrons pass through the focusing anode and accelerating anode, there are plates, Y plates and X plates, and these plates are used to deflect the electron, like whether the electron will go this side or this side. This is in, suppose this is the square, so this is the center. If these are X plates, that is they will deflect the electrons, whether it will come here or electron will come here. Similarly, there are Y plates, and since these Y plates, then they will deflect the spot in vertical direction. So whether the electron will collide here or spot will appear here. So these are determined by these X and Y plates. So this is the this X and Y plate constitute the deflection system, and this complete is the electron gun, which produces highly accelerated electrons. So this grid is used to control the brightness, and these are to control the energy, that is acceleration and focusing anode, and to move the spot on the fluorescent screen. These X plates and Y plates, those are deflecting plates that are used. And why vacuum is present? Because as we saw in case of resistance of the wire, when the electrons are traveling, there are many electrons not a single. Since there is a beam of electrons, there are many electrons. So they will get collided with other particles if the other particles are present in that medium. So when we are creating vacuum in the medium, then there will be very less impurities in that medium. So there will be no loss of electron energy due to collision. So the electron will be effectively colliding at the fluorescent screen only, and they will be producing bright spot. So vacuum is used to. So vacuum is used inside the glass tube. Inside the glass tube, so that there will be no impurities or there will be no deflection in the path of electron. Also, when the electrons collides frequently, then the path will be also different. But here only the path is being changed with the help of these deflecting plates, X plates and Y plates. Now discuss a problem corresponding to this cathode ray oscilloscope. Now the question says, figure shows a bright spot at the center of the screen of a cathode ray oscilloscope. If the X shift and the Y shifts are adjusted such that potential at Y1 is lower than Y2 and potential at X1 is higher than X2, then what will be the possible new position of the spot? So this is a very good question based on the concept of deflecting plates at the deflecting systems. So as we discussed, there will be deflections, horizontal deflections and vertical deflections. So the question is based on that only. So in this question, we can see there is a spot which is placed centrally here. However, when we are changing the biasing, that is the biasing are changed so that the potential at Y1 is lower than Y2 and X1 is higher than X2. Then due to that applied potential, the spot will move in the screen, because the main use of these plates are to is to deflect the path of the electron. So the spot which is appearing at the center of the cathode ray screen, cathode ray oscilloscope screen, then the spot will be changing its position. So what will be the new position of the spot? So you can easily understand what is the function of the deflecting plate. So please think about this question, and after a few minutes we will discuss. So let's discuss this question. So what is given here? Now this is y1, this is y2, this is x1, this is x2. Here is given the potential at y1 is lower than at y2 and x1 is higher than x2. So suppose we consider high means positive, low means negative, because this is the potential and there is electron is flowing because the spot is due to the movement of electron and when the electron collides with the screen, then the spot is produced. So now let's see what will be the effect on the path of electron. Here it is seen the potential at y1 is lower than y2. So y1 will be negative, y2 will be positive. So suppose the electron is flowing, this is y1, this is y2, this is positive, sorry, this is negative, and this is positive. So suppose an electron is going in this way, then the electron will go in which direction? Since the electron is negatively charged, so electron will go towards this because it is positively charged. Now potential difference is such that the potential at y2 is higher because y1 is lower than y2, so the electron will be deflected. So the electron will be in this direction or in below. But again, so the due to this force, the electron in vertical direction, the electron motion will be downwards. But again here there are horizontal components also. So x1 and x2, suppose the electron is going in, suppose this is x1 and this is x2. X1 is higher than x2, so x1 is positive, x2 is negative. So here x1 is positive, x2 is negative. So since x1 is positive, so this is positive, so electron was coming this side, but since x1 is positive, electron will not come to this side, electron will come to this side. So this will be the new spot for electron because since the potential at x1 is higher and x2 is low, then the electron will move towards x1, and since the potential is higher at y2 and potential is lower at y1, then the electron will come towards y2. So x1, y2. So the spot will be in this quadrant x1, y2. So the spot will be in this quadrant. So this is the correct answer. Is there any doubt in this question? Anyone? Because it's a very good question. How the plates are deflecting the electrons? Because the plates are applying some force, and due to that force, so either the force will be in vertical direction or in horizontal direction, and due to that, the path of electrons are changing. Okay, let's go to the next question. Now the question says, by changing the time base of the CRO, we change what? So in CRO, we know this is a x-axis, this is a y-axis. In x-axis, basically there is time. In x-axis, there is time, and on y-axis there is either voltage or current. So therefore, this is a it will show either voltage or this will show current and the time. So when you are changing the time base, then time will change. So t will be changing from t1, t2 like that. So since time is changing, so time is related to which quantity? Time is related to frequency. So here frequency will change. So the frequency of the sawtooth will be changed because amplitude will be fixed because we are changing only this scale. So what is a sawtooth wave basically? So sawtooth wave is like that. It will increasing, then it will drop. So this is sawtooth wave, and when you change the time scale, then the frequency will be changing or frequency will increasing. Here the frequency increased, but when you so here the frequency is decreasing. Here frequency is increasing. So by changing the time base, of the CRO, we can change the frequency of the sawtooth wave. And again, if you see a CRO cathode ray oscilloscope, which result it gives? It gives in DC value, or it gives in RMS value, it gives in peak value, or it gives in mean value. So if you see always, so it gives you the peak to peak values. So from this peak to this peak, and from this peak to peak value, you can calculate other values like RMS values, peak values, and mean value. So RMS value, DC values, and mean value. So the cathode ray oscilloscope gives peak to peak values, and from that peak to peak value, suppose this is 5 and this is -5. So peak to peak value is how much? 10. So this is total 10. So when you divide, the mean value will be 5 because this is 0 here. The mean value will be 5. And we know RMS is how much? RMS value is mean value by √2. So it will be 5 by √2. So it gives peak to peak value, and from that peak to peak value, we calculate DC value, RMS value, and mean value. So these are a few utilizations of cathode ray tube, and today we studied about how the cathode ray tube works and what is the role of these plates, like deflection systems are also role of these acceleration systems. So is there any doubt in this section? Anyone? Yes. So next we have this basic analysis like data collection. When we are collecting data, what type of procedure we should follow, what do we need to do, and then after collecting the data, how to plot the data. Then there are different other techniques like indirect measurement, which is called as calibration, and then how to analyze the error present in our measurement. So in the next week, we will be covering these topics, basic analysis. So is there any doubt regarding any question in today's session? Anyone? Yes, is there any doubt? I think we should stop here and we'll discuss a few more questions in the next interaction session. So thank you all. Good night.